Sampling is the process of taking a continuous time signal and turning it into a discrete time signal. So a continuous time signal is basically anything that exists in the real world, like audio or even images, video, and so on. Our bodies exist in the analog continuous time world, but computers can only store lists of numbers, and lists of numbers are discrete time, what we call discrete time signals. So in order to go from the continuous world that we live in to the discrete time world, which is how computers function, we have to do something called sampling. And sampling is the process of taking a continuous time signal and making a list of numbers that represents that continuous time signal. So let's see what I mean by that. You can see here I have just a generic cosine with some frequency f, and here it is going on and on. And if I want to take that and sample it, in other words, if I want to take that and store it in a computer, what I need to do is I need to go, and obviously there's an infinite number of points that are spaced infinitely closely together. So I can't store all of the blue points, but what I can do is I can sample it. So I can take individual points and I can store those values. So if I pick the y values of all these red dots and put them in a list, you can see that if all I had was the red dots, I could probably figure out that what I had to start with was a cosine. So what I want to do is just store the red dots, and then that's enough information for me to know that what I had started with in the first place was the blue signal. So if I have the red dots, I can work my way back to the blue signal. That's what we mean by sampling. So let's talk mathematically a little bit about what happens. Let's assume that I collect samples at a certain rate, and let's say that I collect samples at a rate of f sub s. So that's my sampling frequency. And the units of that is samples per second. And if that's true, let's also notice that if I take the reciprocal of that, I wind up with t sub s, which is the sampling period. And that's the time between samples. Okay, that's in seconds. That's how much time you have between samples. So if I go back to my picture, I can see that my first sample, well, it'll actually be my 0th sample, that will occur at time 0. What about this sample? That's my first sample. That will occur at time t sub s, because t sub s, again, t sub s is the amount of time I have between samples. This sample will occur at time 2t sub s. This sample will occur at time 3t sub s, and so on. In general, what my list of numbers is going to tell me is it's going to be cosine of 2 pi ft, but instead of allowing t to be any value of time, I'm going to restrict myself to values of time that are integer multiples of t sub s. Okay, I'll have the 0th sample, the 1th sample, the 2nd sample, the 3rd sample, and so on. So I'm going to restrict myself to integer multiples of t sub s. And keep in mind that t can be negative. So in other words, if my signal went backwards, I could have the negative 1th sample, the negative 2nd sample, and so on. Okay, so in order to work this into a slightly more standard configuration, I'm going to rewrite this as cosine of 2 pi f. And then I'm going to notice that t sub s is the reciprocal of f sub s. So I'm going to take my t sub s and rewrite it as 1 over f sub s. And then I have the n. And then finally, I'm going to compress this 2 pi f over f sub s. I'm going to compress that into capital omega. That's a capital Greek omega. 2 pi f over f sub s. And finally, I'm going to arrive at cosine of omega n. So in exactly the same way that cosine of omega t was my generic continuous time cosine. Now I have cosine of omega n, which is my generic discrete time cosine. And you'll notice that it's not a function of time anymore. Now it's a function of n, where n is the sample number. Okay, so I reflect that in two ways. First, I use n instead of t because there is no time anymore. We just have sample numbers. And then I use the square brackets instead of the round parentheses. That's by convention, just so that everybody's aware that we're talking about discrete time and not continuous time. Good. So the next thing I want to do is let's talk units. So the units of n, well, we know n is an integer, but it's referring to the first, second, or third sample. So the units of n is samples, which means that the units of omega has to be radians per sample. And the reason it has to be that way is because if you do omega times n, the units of samples cancel, you're left with radians, and that's good because you're only allowed to take cosine of radians. So those are the units. Okay? Now, we're going to end this video with a brief example. So in the brief example, let's assume that we have a cosine of, that's not very pretty, but I think it'll get the job done. Let's assume that this is cosine of 1 hertz. So 2 pi times 1t. And let's say we're going to sample it 5 times a second. Okay, we're going to sample it at 5 hertz or 5 times a second. So that means I'm going to have a sample at t equals 0. Okay, so if that's 0, this is t equals 1. Then my next sample will be at 1/5 or 0.2 seconds. So that'll be about here. So that'll be my 0th sample. Then my first sample will be at 0.2. Then my next sample will be at t equals 0.4, 0.6, 0.8, and then finally I'll get another sample at t equals 1. Okay? So let's work out the math and see what this tells us. So according to what we've just come up with, this the red dots should have a continuous time frequency. The red dots are a discrete time frequency. The red dots are a discrete time signal whose frequency is 2 pi times 1 over 5. That's according to the formula, which comes out to let's just say 2 pi over 5. And that sort of makes sense because in essence what it's telling us is that every period I have, let's count the samples per period. Every period I have 1, 2, 3, 4, 5 samples, and then this will be the first sample of the next period. So 1, 2, 3, 4, 5, and then so on. So every period has 5 samples, and it kind of makes sense. If every sample gives us, if we get 2/5 pi radians per sample, so 2/5 pi is my radians per sample, that's my frequency, times 5 samples per period, then I get 2 pi radians per period, which is always, that's a constant, that always has to be true, so that checks out. Okay, in general, in the discrete time world, the equation is that 2 pi omega, the frequency, equals 2 pi over the period, where the period is given in samples. Okay? So, in the next video, we'll work on figuring out what are the limitations on values of omega and how many samples you need in order to get a clean representation of your continuous time signal.